Well, yes, hello. I'm not Paul Bell, I'm Dave McCann, and I'm here to talk to you about some work I was involved in last year, which was funded by the NERC Marine Renewable Energy Knowledge Exchange Programme, and this was conducted between the National Oceanography Centre, where I work, and McCann Limited, who, as many of you know, are set to be installing demonstration array of turbines up in Pentland Firth, in northern Scotland. This should be known to most of you by now. The red polygon up there is McCann's Crown Estate lease, and to the right there's also another one in Pentland Firth over Nessa Duncansby, which is Scottish Power Renewables. But we focused over the McCann site. The project, as I said, was set up by the NERC KP programme. And the primary aim was to showcase to a marine renewable energy company the state-of-the-art in ground-based remote sensing of tidal currents using X-band marine radar. They're very interested in this because they need as much context as possible of their site in order to de-risk their installation, but also to give a better handle resource estimation. Now, traditionally you do those kind of things with in situ underwater surveys with things like ADCPs, and in areas like the Pentland Firth this is incredibly expensive. It also gives you only an idea of what's happening very locally. These are very dynamic areas, so we came in to hopefully give them a bit more contextual information. We were provided with 2 ADCP surveys to validate our radar targets as well. Okay, so the field deployment was at the end of a field in a place called Hoona. It's overlooking the McCann site and the rest of the Inner Sound of Stroma. It ran between March and June for 91 days straight until the generator died unexpectedly. The radar you can see up on the top of that scaffold there. It's just a standard marine radar you'd find on a boat, Kelvin Hughes, with a 2.4 horizontally polarised, horizontally rotating antenna, and it rotates once every about 2.5 seconds depending on wind. And we record 5 minutes of data, which is 128 images. Those are then digitised by a separate computer and then saved timestamp. And this happens once every 20 minutes. The scaffold's about 12 metres above mean sea level. We were on top of about an 8-metre cliff. And the equipment ran off batteries. You can see in the image there's a white box provided by a company called Off-Grid Energy in Rugby. This is just filled with lead-acid batteries and some intelligent electronics. And the idea was that because we couldn't be hooked into the national grid this far from the farm, we'd run off the battery bank and this would be topped up by the generator. And this reduced our maintenance time, fuel consumption, everything. So it was a very novel energy solution, we thought. But yeah, the raw data was processed after the fact rather than being processed on site. This is something that we're aiming to do in the future. But this is all post-processed, and we generated, I think it was about a terabyte over the whole 3 months, actually, not a terabyte. So this is what the raw data looks like. Just to give you an idea, the blob up at the top is the Isle of Stroma. You can see mainland of Scotland down to the south of the image. The white box is our analysis area. We'd like to analyse the whole of the data set, but it took 3 months to analyse 3 months of data in the white box. You can see the McCann lease site, and then the 2 symbols are the ADCP locations. So this is an example of very bad data. Now what we do is we use images of waves on the sea surface. Now Paul mentioned sea clutter, and this is a phenomenon where you can see the waves individually in X-band radar images. Now if you've got these time-stamped and stacked up, this is an example of fantastic data. You can start getting a handle on the wave spectra in a discrete analysis area. And it's this information on the wave spectra that we then use for the rest of our analysis. But this is just this is all of the input that we get, just these radar images. So the NOC current analysis, as Razor mentioned in his talk previously, is based on the Doppler shift of surface gravity waves based on an underlying current. And the idea is if you've got this time-stamped series of images, you can start picking out things like the wave number k and the wave period or frequency sigma. Now, if you've got enough of a spread of k and sigma based on different waves in each spectrum, you can start getting a handle on where these sit on, for example, we've got a one-dimensional example over on the right there. This is the dispersion relation. So if you had no current, the dispersion relation would look like the black line. But as soon as you start having a current, this black line is shifted, this Doppler shift. So if you have, critically, if you have a good spread of these wave measurements, you can start working backwards through the dispersion relation, and you can pick up the tidal current. This works on a box 200 meters across, so it's an area measurement that's then centered in the middle of this box. And this is going to be important for later on. And this box is shifted stepwise across the grid, so that's how we can build up a map of current. Now this area problem is very important because subgrid scale effects are not accounted for in this analysis. If you've got strong horizontal gradients in currents, which you do get in these areas, it can really muck up the analysis. So we're assuming wave spectral homogeneity and also, to an extent, current homogeneity across this grid set. And this must be taken into account when you're comparing this area measurement with something like an ADC. So as I said before, we're trialing near real-time processing. Now to cope with bad data, we've developed some unique quality control parameters, and these are calculated as the data is being generated. And these are used to chuck out just bad data from bad spectrum, basically. But the consequence of this is that it varies across the site, and this is a combination of both whether or not you had good waves in, for example, the western area of the site. We had predominantly easterly waves through the whole of this deployment. They didn't quite penetrate into the Inner Sound of Stroma. There's also a range effect because radar is a microwave camera, essentially, so at longer ranges we don't quite see as much of the wave as we do in shorter. So you can see down in the bottom right hand corner we keep about 80% of the data after quality control, but unfortunately over in the western areas we're down in the sort of 20-30%. Again, you can see where the ADCPs are. So for comparison purposes, we've only got maybe a month's worth of data, and then a small amount of that overlaps with the ADCP survey. This is an example of what you get on a really good day. So this is from the bottom right-hand corner of that plot. Up at the top, we've got the current magnitude, total current magnitude, and then the U and the V components. You can see days where there's no data. This is when we don't have waves. So the analysis is completely reliant on the presence of waves. So of course, as we get into June and everything starts to calm down in the Pentland Firth, well, relatively, and we don't get any data. But this is an example of what you can get if you've got good waves. So this gets built up into a map. I would have a video of this which looks really impressive, but it takes a good 3 minutes to run through in that time. But this is an example of a snapshot in the ebb. You can see the greyed out areas are the areas where the quality control was kicked out of vectors. So if you imagine over time, over in the west, and especially over to the north, where we've got some really strong subgrid scale effects from the Isle of Stroma, you have a very bitty record of current. Yeah, unfortunately the westerly area was mostly sheltered. We did have some big westerly wave events that cleaned up the data there, but it's mostly easterly. So like I said, we had 2 ADCP surveys for validation. Now, it's very important when you're comparing these two, not just that you've got to realise you're comparing an area measurement and a point measurement, but also there's no agreed relationship between the flow speed that the radar sees, i.e. the flow speed that the waves are feeling, and what point in the water column that corresponds to. Now the waves technically should be feeling the bottom, so it's going to be some kind of integral of the water column. So I've compared just the depth average flow of the DCP with the current waves. But again, there's no like-for-like comparison possible here, so we shouldn't expect the world from this. However, we do get something fantastic. Got the depth average current speed up at the top, and then the U and the V components. And you can see that most of the errors are coming from the V velocity components. We're just not resolving them. Now this is down to a number of effects, mostly subgrid scale effects, but also the ADCP data, the black line. It's not particularly tidal in that area in the V component. There's a very, very strong mean velocity. So there's some other process that we're not picking up. But where it's very rectilinear in the U components, we're really picking them up. And again, for the other ADCP series, it's fantastic. But again, there's something funny going on underneath the RF sky. If you look at it like this, I think that's fantastic. We very rarely see lines like this with radar. The slope up in the top right-hand corner there, in the U velocities, this may have something to do with the depth, penetration of these waves. I'd like to talk to people about this if they've got any handle on the physics of that, because we're quite interested in how we're going to pick that out. I'm going to have to rush through this a little bit. Hopefully a lot of you know about tidal harmonic analysis. But one of the things you can do with this data set is you can start doing not just a harmonic analysis of a one point, but you've got time series all across your domain. They're very bitty, so you might not get too much out of them where the data's poor. But you can start pulling out maps of tidal harmonics. Now, our analysis is just based on U time, because it works with bitty data. It worked out quite well. Now, we can't stay on this for too long. You're going to have to take my word for it, but it's a relatively good comparison with the same analysis applied to the ADCP surveys. We're both explaining about 98, 94, 97% of the variation of the tide with the constituents that we pull out from the harmonic analysis. But you make maps like this. The M2 one is especially good, I think. These are just the amplitudes of the 4 top constituents in that area. You can see up to the north of the analysis area, everything starts to degrade and get very noisy. And again, these are the subgrid scale effects that are ruining the current analysis and therefore feeding into a bad one. And the phases, perhaps not particularly interesting, but they match up with what the ADCP. Okay, so one of the major conclusions of the project was that X-band radar may not be very good at giving you very accurate tidal current information. The one thing it is very good at is giving you a wide context to your site. And considering the cost of in situ surveys, this could be a great tool to figure out exactly where you'd like to place these costly in situ surveys. The total cost of the project was minimal compared to an ADCP survey, for example. And we got 3 months of data because the generator packed in, but potentially this could be a survey that goes on almost indefinitely, as it has been going since 2011 up at EMAC. So there's a lot of value to this kind of survey. Excellent validation. Well, we're very pleased with it anyway, and it lends confidence not only to this data set but also to these kind of surveys we want into the future. And McCann are currently using this data to help de-risk their turbine placement ahead of their the installation either end of this year or next year, by the sounds of things, which is exciting. I think I've covered everything, so I'll leave it at that. And that I've got the copy of the report. It's publicly available, but I've got a few copies with me, both in paper and on 50 little thumb drives if anybody wants. Thank you for listening.
Okay, thank you. We can take a question. Please.
Oh, sure. Actually, the scaffold is really essential in getting a good range of data. So with a high scaffold, with the current settings, we have a range of 4.8 kilometres. But with a higher power setting, you can double that. Paul's been doing quite a lot of work down in West Kirby Sands, doubling the range, and it does seem to work quite well at long ranges. So, but this is all work in progress. With good waves as well, you can pick up these currents good 3 to 4 kilometres with a grid resolution of 300. I should. This is you're actually picking up the capillary ripples on top of swell waves. That's the imaging process. But yeah, these are big swell waves.
Okay, thank you very much. We'll close this session in a moment. Can I just remind authors to see me after the closing session to sign a consent form if they will. So thank all the speakers in that session, and we'll move on to the closing session, and Arnie's going to give a little bit of organisational information. Thank you.